Okay, so to understand how the electric field works, I'm just going to quickly go through the expression that we have seen in class. So this is basically what it is in its two forms, one using a unit vector, I'm going to explain, and one using a normal vector. You can also get the magnitude of the field with this, which is the same as just taking the magnitude of this part. Since the magnitude of a unit vector is just 1, and then you just take the absolute value of the charge, since you do not want the direction. Because if the charge is negative, then direction's going to be inwards in the opposite direction as your radial vector, your radius that points from the central charge with charge q to the position that you want from the electric field. So if q is negative, it points inwards. If q is positive, it points outwards, basically. So just here, this 1 over 4 pi epsilon naught, that's just a positive constant. Don't worry too much about that. Q is the charge of the point charge that we want to do. This only works for a point charge though, or as we can see in some of the lessons, a spherically symmetric charge distribution. Then we can just get r is the distance from the position from the point charge. That's the same as the magnitude of our radial vector, or radius or position vector. And then yeah, r is just the vector from the point charge to the position. So it just points, r is usually from the center. You usually put the charge at 0, 0 if you can, unless you have multiple. And then you just calculate that. And then the unit vector we just define as the vector divided by its magnitude, so that its magnitude just becomes 1. So this only indicates direction. It's only a direction vector basically. So that's what the electric field equations that we have so far seen do basically. Okay, so the next concept that I want to tackle is the one of symmetry. It's going to be essential for at least the rest of Physics 144, but also physics further on. Symmetry helps us to simplify systems so that the math we have to do is less for still getting the correct answer. So if we look at the way we would approach it, as we've seen in the lectures, it's about thinking how you can transform the system so that it's still the same. So for example, a circle rotated about its center will still be the same since it's a circle. So therefore, our entire system has rotational symmetry. So also, no matter where you go you go in the field, it has to be the same at the same distance from the center, since you can always rotate that. But that's a bit of a more complicated way of doing something if you just want to get some cancellations. So one of the things you have to realize is that if you have a point here, then there's going to be a charge, but directly in the opposite direction and the same distance. My circle's a bit wonky, but at the same distance you'll get the same charge. So the same charge at opposite sides, they will just cancel out, because this will pull it with a certain force in this direction, and then this part will pull it with the same force but in the opposite direction. So it will just cancel out. So if you have something like a circle, or any part of the circle, as long as the opposite sides are identical. So we can even maybe take out maybe a part of this circle. Just imagine that's the opposite sides. But this will still have 0 electric field at the center. Because for every piece of charge that's on this part, there will be an equal part on this segment that'll just pull it in the opposite direction. So since it's opposite direction, same magnitude, that just means it's 0 at the center. Note it's not going to be 0 at any other point, but here it will be. Then we can also go to something like these plates. So if I have a plate or just some bar or something like that that has charge, also the same charge. If it has opposite charges, then obviously they're going to have a cumulative effect at the point in the center. But if they're the same, then for each part up here that's pulling it up, there's an equal part down here pulling it down. So it's just going to be 0. You can also imagine rotating this 180 degrees to get kind of the same effect. But yes. Now, there are also some more complicated ones. If we just look at this triangle, for example, that's still going to cancel out, as long as this is a equilateral triangle. So all our angles are 60 degrees, then this is still going to cancel out because it's a symmetric distribution. You can rotate it, and if each one of these charges are identical, and this is the center, although I didn't draw it very well, then at the center, then it will be 0. Same thing for the square. There you can imagine it like this, or you can imagine this having a negative, these two together having a positive effect in this direction, and the bottom two having an effect downwards, and them cancelling out. That's also useful for when we go out of the plane, say we go 3D and we have a point outside, now this will feel a force. If this is positive, say, and my charge is negative outside, it will feel a force into the plane, because it won't feel a force in that direction or this direction or anywhere as long as it's on this center. But since it's over here, it has a net force in this direction. So thinking about the way these things cancel out in components is often a better way than thinking in total, because these two don't quite cancel out, for example, in the y direction, but they cancel out in the x direction. But then this will cancel out the rest of that, and since it's lined up, it has no effect on the x direction of the force. Same thing here, these two cancel out in the x direction and x direction, but they still have y components between the two of them, but these y components are opposite, so they cancel out here. If you go here, however, then you suddenly have the z components of all four of these that contribute the same, and you can count them together to get the magnitude of the field at that thing. So that suddenly goes from a calculation where you have to calculate 4 charges to 0 if you're on the plane and only 1 if you're outside of the plane. And that's why symmetry can help us a lot in a lot of these calculations. It simplifies everything. Next, I want to talk about how we do integrals. If you're not talking about point charges, then Coulomb's law no longer applies. So we have to do something a bit more complicated. But since we want to go from Coulomb's law, we want to go from things that are almost point charges and basically just sum up all of their contributions. Now, if you know integrals, you know that the integral is just a sum over a lot of small parts. So first we want to introduce lambda, which will be our charged density at a point. Lambda is just used for in one dimension. So if you have 2 dimensions, 3 dimensions, there are different symbols we usually use just to denote that it's different. So if we take lambda and we multiply it by x, which is a part of this a, so we can have this a length be different values, so it can be a straight line, or we can have like a curve of a circle. To get the length there, you just take the radius multiplied by the angle in radians, and then you get the arc length of that part. And then you have the a, you can substitute that in there if you have the total charge, or they'll just give you the charge density. If you then multiply that by a certain distance, you will see that that will give you the charge on that distance, not the entire charge. So if we use d before a variable to just show that it's infinitesimal, and we only want the small part of it, then if we take lambda times dx, which is just a very small distance, we will get a very small charge, dq. Now if we go back to our normal expression here for the Coulomb force, or the electric field due to a point particle, and then we just, instead of using the electric field and using a normal point charge, we're going to use an infinitesimal part of the electric field, and we're going to use an infinitesimal part of the charge. Now we can just substitute dq in here, since we already have an expression for that, and we just plug that right in there. Nothing too complicated. Then we take the integral on both sides, since we want to sum up all of these very small contributions, because we don't want just small contribution of the electric field, we want the entire electric field at that point. So we're going to sum up over all of those small contributions, and then just use the integral here. We can put this outside of the integral, since it's just a constant. It's not going to change anywhere. So in the integral, if something is not a function of your integration variable, which is this here, the dx, if it's not a function of x, then we can just pull it outside. Now you're left with this. So lambda can be a function of x. It's not always going to be. Normally it's not going to be, but there can be case that it is. Your radius vector, your position vector, will almost always be a function of x, otherwise you're not really doing anything. Your radius, just the number, isn't necessarily a function of x, since if you have something like a circle, your radius is always going to be constant. So if you always have a constant radius, you can also pull that outside, which further simplifies the integral. Then if you have this integral, use either basic integral rules to solve it, or you can, if it's too complicated, you can use some of the example integrals that we have on the page that will show you how to solve some of them if they have a certain form. So you just need to learn how to recognize those forms and then just use the document to find them. And that's basically the idea behind finding the electric field for a continuous charge distribution and not just a point charge. I just quickly want to add for that previous part, where I put the formula lambda equals q over a, that is just under the assumption that your charge distribution is constant, which is going to be valid in almost all circumstances. So if it's not valid and that formula isn't valid, then they have to probably give you a function lambda and then just ignore that formula. And then your integral is going to be a bit more complicated, as I showed. But that's just something to mind. Again, so I want to quickly run through an example. It's just a bar with total charge q. The bar starts at x equals 0 and ends at x equals a. And we want to know the electric field at x equals minus d. So what do? First, we parameterize the charge distribution here. So this is a constant charge distribution. We can just use lambda equals q over a, and that gives us lambda dx equals dq, just as I showed before. Then we also use, as before, this just this formula. I chose to use the one with the unit vector in this one, since it's only one dimension, and a lot of things just cancel out nicely that way. You can also just use the r cubed, and then in your first step you'll see it'll just cancel out. So then you do the integral on both sides. Since you have your integration variable here, you can put it's from x equals 0 to x equals a, and then you have that. Then if you do the integral, you can use u substitution or something if you don't trust me, but the integral of 1 over x plus d all squared dx is just minus 1 over x plus d. That's just a normal integral. That shouldn't be an issue. Then you can take the lambda and the I hat, which is just the unit vector in the x direction, pointing that direction. You can take that out since that's a constant, so we have all the constants here. And then we have our result, and we have to substitute in the values at the bounds, which is x equals 0 and x equals a. So we want to do x equals a of this term, where we put in a instead of x, and then minus where we put 0 instead of x. Since this is a minus, that's the same as putting a 0 here where that's positive, so that's just 1 over d. And putting an a over here where this is negative, and that's a positive, so it stays negative. Then we have a negative, well, same as minus 1 over a plus d. Then there's something we have to note here. I went from lambda to q over a. In these types of questions, you always want to come back to the total charge, because it's going to tell you more about the behavior of the system, and that way you can check that your results are actually correct, and most of the time that's going to be what the lecturers want. So then we can also do another thing, which is go from this form, which we see here in brackets. We want something that looks a bit like 1 over d squared, since we know that if we go really far, or this a is very small, this thing is going to start looking like a point charge. And we know a point charge, the electric field drops out off like 1 over r squared. So we want to have something like that, or in our case d squared, since that's how we parameterized our distance from this rod. So if d gets really big or a gets really small, we want to get 1 over d squared. So we know that we can take this further. Now we can just do our normal thing where we combine two fractions, and you get this, and you see it nicely cancels out. You get a over d squared, which is nice, plus ad. So now in this case, where a gets really small, we're going to see the a cancels out with this a at the bottom, so don't worry about that. But if we get d really big or a really small, if d is very big, then d squared is a lot bigger than a small number times d. So that's going to be almost exactly 1 over d squared, so it's going to act like 1 over d squared. And if we have a very small, then this term is going to be very small, and we're going to get almost exactly 1 over d squared in that case. So that's also what we want. We have the q over, we have something that looks about like 1 over d squared if we go far away, but close it has some different behavior. And then we have the I hat, since the field's going to be in that direction. And then at the end we just have the constant. So that's basically all there is to a simple calculation like that. I think I'll do one more just for a circle, so we can see how we're going to parameterize some of these things differently. But that should be it. So I just realized, obvious sign mistake. We want this field to go in the left direction, since if this is positive and we have a positive charge here, then it's going to go to the left. So we have to have instead of the normal radial vector in that direction, we want it in this direction. Just a simple mistake, since at this point we know the charge is here and we are here, and we always want the vector to point from the charge to us. So that was a stupid mistake by my part. and one that I hope you will not make. So since it's going from this direction to this direction, it has to be negative. So we just put a negative everywhere. Since we're just going to replace here the r hat with minus r hat, that's the minus there, the I hat with negative I hat with negative I hat with negative I hat, and I hat with negative I hat. And then we get the hopefully correct answer here. I'm not going to go through the entire example again, but I'm just going to show you the ideas behind that. So if we have a ring of charge right here, that's very thin, so you can basically approximate it as a line. It's a distance r from the point that we want to know, and there's an angle that I'm going to call alpha between these two lines. So first things we want to do is we just want to put the x-axis on one of these lines. That's going to make it a lot easier, and then the y-axis obviously just perpendicular to that, so that's not necessarily on the other line. Now we're going to see, since this length, as I already showed, is r alpha, we get that the charge distribution is going to be the total charge divided by r alpha. Now we see that it's a bit different than the normal thing, where instead of alpha, if we put it in very small angles, we can just call that d theta. We want a different variable there, and so we multiply both of these to these sides and then make it infinitesimal. So we replace alpha with d theta, and we replace q with dq with the small q. So then we get this expression. So now we start with this one again. Once again, I want to use the unit vector, because the unit vector in polar coordinates is very simple. It's just going to be cosine theta times the I hat plus sine theta plus times j hat, because I just put the x-axis at theta equals 0. So now we also just want to integrate from 0 to alpha over d theta. You're going to see that. So we replace dq with lambda r d theta. So lambda r d theta, here you put the lambda r, and d theta is going to come at the end of the integral. Inside the integral you just put r hat, since the distance you are from the center is a constant, so you can ignore that inside the integral. Now you might want to immediately cancel out this r with that r squared, but that might not be the smartest thing to do, because if we see here, if we multiply r to both sides, lambda times r is just q over alpha, and we also always want to get q back, so then we get this. Now once you have this, if you just basically evaluate this, it's not too difficult. You know, sine theta disappears at 0, cosine theta is just 1 at 0, and then depending on your alpha value you can substitute this, and you get the x and the y values. So the final part shouldn't be too bad, and you can still see that this falls off with r squared, so it still behaves as we expect it to do. So I hope that covers most of the conceptual difficulties many of you had with the first 2 weeks of work from Physics 144. Any questions that you want to send me, or comment or anything like that, please tell me if this helped you. That'll at the very least inspire me to make more of this if this actually helps. Any constructive criticism, please just leave a comment or WhatsApp or whatever. I really do want to improve. And then, yeah, any questions through the week, anything you want specific attention on, or any suggestions, please feel free to leave it wherever you like. Thanks, guys.